Assalamu alaikum. I am Sabab Sal from University of Agriculture, Faisalabad. I just completed my master's degree under the supervision of Dr. Shazia Shukrullah. The title of my research work is The Synthesis of Luminous Spotted Zinc Sulfide or Cadmium Sulfide Photocatalyst for Catalytic Hydrogen Production from Non-Thermal Plasma Exposed Hydrogen Sulfide. These are the outline of my research work which I will describe step by step. Now I will explain the research background through some questions. Number 1. Why is hydrogen gas important? Hydrogen is used to make ammonia for fertilizers, refining metals, and methanol for making artificial materials like plastics. Hydrogen is also used as a rocket fuel where liquid hydrogen is combined with liquid oxygen to produce a powerful explosion. In the food industries, hydrogen is used to turn unsaturated fats into saturated fats and oils, including hydrogenated vegetable oils like margarine and butter spreads. Some other uses of hydrogen are in the steel welding process, the power industry, and electricity generation. As we know, it is used in every field of life, therefore, it is essential to understand how it is produced. What are fossil fuels? Fossil fuels are made from decomposing plants and animals. These fuels are found in the Earth's crust and contain carbon and hydrogen, which can be burned for energy. In fossil fuels, coal, natural gas, and oil are included that are used as energy sources in the electricity and transportation sectors. Fossil fuels are non-renewable, means that their supply is limited and will eventually run out. What is the hydrogen production rate from fossil fuels? Nowadays, 100% of hydrogen is produced from fossil fuels that decrease the natural transportation. What will happen if fossil fuels run out? It will affect global transportation and international trade because our major transportation system, including trucking, rail, and sea transportation of goods, depend greatly on fossil fuels. Without diesel and bunker fuel, large-scale international trade would have no choice but to shut down. How much fossil fuels are left? From literature study, it is clear that fossil fuels will run out in this century. Oil can last up to 50 years, natural gas up to 53 years, and coal up to 114 years. Non-thermal plasma technique. Non-thermal plasma is electrically energized matter in a gaseous state and can be generated by passing gases through electric field. The field energy causes a free electron to accelerate and ionizes the gas atoms and molecules, which release more free electrons that in turn provoke new ionization. The advantage of non-thermal plasma is that it can be generated at low temperatures. However, in general, the relatively low temperature of non-thermal plasma allows its combination with catalytic processes. Dielectric barrier discharge reactor. Dielectric barrier discharge plasma is one of the most common methods of non-thermal plasma generation. A DBD reactor is composed of a set of electrodes with at least one dielectric barrier between them. Due to the presence of dielectric barrier, higher voltages are required for DBD to generate a high electric field between the electrodes that is necessary for plasma formation and causing breakdown in the gas. Non-thermal plasma can also be generated in several ways, including electrical corona discharges, radio frequency discharges, and microwave discharges. But the advantage of DBD over others is that DBD once produce a homogeneous discharge with lower energy consumption, so resulting in no spark formation inside the streamer channel and overheating. Additional advantages of DBD reactors are their scalability, effectiveness, and low operational cost. To reduce the use of fossil fuels, different transition metals were used for hydrogen production. In our research, we used chromium-doped zinc sulfide photocatalyst. It showed 100% hydrogen sulfide conversion. Due to the closed ionic radius of chromium and zinc, it is easy for chromium to substitute zinc and the penetrate host lattice of zinc sulfide. Some other transition metals like nickel doped zinc sulfide, silver, iron, and copper doped zinc sulfide were also used for hydrogen production but not showed the best activity research than chromium doped zinc sulfide due to their physical and chemical properties. The main objective of this research is to produce hydrogen from hydrogen sulfide in non-thermal plasma that will be used in the automobile to generate electricity and heat. Preparation of photocatalyst. The photocatalyst was prepared by the co-impregnation method by adding zinc nitrate, chromium nitrate, and aluminium oxide into distilled water with continuous stirring. The prepared solution was filtered and then dried at 120 degrees Celsius temperature. The dried material was calcinated at 450 degrees Celsius and argon gas passed through the furnace tube. After the crushing process, a fine powder of catalyst was formed. This is a schematic diagram of DBT setup used for hydrogen production by cracking hydrogen sulfide molecules over the composite catalyst. DBT plasma assisted hydrogen evaluation. The DBT plasma was sustained with a fixed AC source of 10 kV where plasma produced species and UV radiations were used to activate the catalyst to break the hydrogen sulfide molecules under ambient conditions. The aluminium oxide supported chromium doped zinc sulfide semiconductors. Catalyst was tested for hydrogen evaluation for hydrogen sulfide gas using a single-layer DBT system. The discharge volume of the dielectric battery discharge reactor was 22 ml. One end of the battery was attached to the wire and the other to the dart. About 10 grams of catalyst was loaded in discharge column. At the same time, the gases was passed through the loaded column. The gas product of the reaction in the discharge column was analyzed by a gas analyzer. The crystallographic structure of a material, grain size, band gap, functional groups, peak appearance, and electron-hole combination rate was observed by these characterizations. The XRD results of samples are shown in figure. The diffraction peaks were found at 2 theta located at different angles. The analysis represents the characteristic peaks at maximum absorbance at 56 degree of 0.30 molar ratio sample. The peak showed that chromium ions are homogeneously doped into the zinc sulfide lattice as substituent. The grain size of nanoparticles were calculated by Shearer equation. A hexagonal cubic spheroid structure of particles was observed by analysis. FTIR is the technique used to obtain an infrared spectrum of absorption or emission of a solid, liquid, or gas. FTIR can be used to collect high spectral resolution data over a wide range. It is used to recognize the occurrence of different functional groups, peaks appearance, and compound classes present in a sample. As shown in the table, peaks are found in the group frequency region within the range 3700 to 1531 of wave number, and the fourth appeared in group frequency region. The appearance of these peaks is strong, medium, and sharp, which belong to different compound classes. The absorption spectra of catalysts were examined by UV visible analysis. The absorption edges at 367, 376, and 379 nanometer, corresponding to 0.20, 0.25, and 0.30 molar ratio of photocatalyst. In figure, the molar ratio of 0.30 catalyst showed a superior shift in absorption edge towards the visible region in contrast to other samples, showing a maximum absorption of up to 379 nanometer. The concentration of doped chromium had a pronounced effect on the optical properties of zinc sulfide catalyst and witnessed a significant redshift in the absorption of chromium-doped zinc sulfide. The bandgap values of samples are inversely related to the doping concentration of chromium. As the concentration increased, the gap energy decreased from 2.68 to 1.69 electron volt. The next analysis is STEM. The STEM analysis provides information about the surface morphology of samples. The dark area in images A, B, and C shows the maximum resistance of nanoparticles. Apart from this, the particle size is also calculated from it. The values of average particle size of all catalysts are shown in graphical representation. The catalysts were further characterized with the PL technique to determine the extent of the photo-induced electron hole recombination rate. Principally, high PL emission intensity represents the rapid recombination of charge carriers. Figure shows the PL emission spectra of chromium-doped zinc sulfide catalyst measured at room temperature and an exciton wavelength of 325 nanometer. The chromium doping has successfully altered the surface of the zinc sulfide and promoted the migration of surface carrier, causing the increment in live harvesting, which is consistent with UV visible results. The chromium zinc sulfide catalyst demonstrated the lowest emission intensity compared to the other two catalysts, identifying its effective suppression of charge carriers. Hydrogen sulfide decomposition into hydrogen and sulfur. The catalytic performance of chromium zinc sulfide catalyst samples was evaluated for hydrogen production under non-thermoplasma treatment. The catalytic performance of undoped zinc sulfide and aluminum oxide as a spotted material was also presented. All prepared chromium zinc sulfide catalysts showed better performance of hydrogen sulfide conversion than that of pure zinc sulfide and aluminum spot. The chromium zinc sulfide catalyst with a mole ratio of 0.20 showed the highest decomposition of hydrogen sulfide. The results after comparison showed that hydrogen sulfide conversion varied for different molar ratios. The catalytic activity greatly depends upon the dopant concentration because it initially increases and then decreases with the dopant content. Hydrogen production rate with chromium zinc sulfide of 0.20 molar ratio catalyst. The long-term hydrogen sulfide conversion reaction of 0.20 chromium zinc sulfide catalyst is shown in figure. The hydrogen valuation shows a maximum value of up to 15 R and thereafter starts to decrease over time. 3 different readings were noted at different periods. The hydrogen valuation decreased from 100% to 94% over the chromium zinc sulfide after 22 hours of the reaction time. A decrease in hydrogen production over time might be due to the deactivation of photocatalyst. Conclusion: a chromium zinc sulfide catalyst of different molar ratios was prepared by co-impregnation method of hydrogen production. Catalysts have hexagonal cubic spheroid structure with an average band gap 2.28 electron volt energy and average particle size 81 nanometer. The least PL intensity was observed by minimum doped catalyst. The 100% photocatalytic activity was observed by less doped photocatalyst. Thank you.